power together. So I'm going to show you, kind of got the basics of this input shaping idea. I think a lot of you have maybe seen this before, what Dr. Hong says. Let's look at some examples of this in application, so I can maybe convince you it still works. So here's actually a crane that's at Georgia Tech. There is about 4 meters of cable between the crane hook here and the trolley that's overhead. And then actually, what Dr. Singhos is driving this crane with is a crane pendant. So still most cranes in the world are driven by these pendants, where you push button forward, reverse, left, right. Okay? And what he's going to try to do is basically just pick this thing up and move it over, and then move it kind of into the board and set it down. So a pretty simple crane move and pretty representative of what cranes do. Pick something up and put it over there and put it down. Okay? And you'll see that even this really simple move, he picks it up and starts moving, you can get quite a lot of oscillation pretty easily. So the way this is handled in most factories, kind of state-of-the-art control of cranes in factories, is one, to move really, really slow, to move much, much slower than this, and then to have 4 or 5 of your friends come hold on to whatever you're trying to move. That doesn't work so well. So if we can turn on the input shaping instead, we can take the same crane 30 seconds later and move it without any oscillation at all. So this is just a ZV shaper on that crane. So for the crane, we know the natural frequency fairly well, because it's square root of G over L. It's just a pendulum. Right? So we know L pretty easily. We know that frequency with some knowledge. In my lab, we've been working quite a bit on these systems called cable-driven parallel manipulators. Okay? You guys may have seen, I think they have it here for soccer matches, called the SkyCam. It's a common, so in America we have this camera on the American football field that's suspended from cables in the stadium. And by pulling on the cables, they can move the camera around the field really quickly and take pictures of football. It's really kind of interesting. But what we are doing is looking at a similar system to that. So we have some kind of robot here, maybe, some inspection, some camera, some sensors that are suspended from cables to these winches that I can control. So I have these 4 points where I can reel in my cable or let some cable out to control the position of this thing. But these cables actually can be tens or even hundreds of meters of long. So even if it's a steel cable, you can get a little bit of stretch if it's 100 meters long. Right? And then basically, even though it's a steel cable, it's still a string. So we can get some vibration, string type vibration in these cables that cause vibration here. And then depending on what I'm doing here, I'm just hanging from strings. So I don't have so much way to kind of control what I'm inspecting. But for us, what we're doing, we're actually working with a company in Japan that I do some research with. And maybe take this kind of system and hang it underneath a bridge. Right? And instead of taking pictures down of American football, I put my camera up at the bottom of the bridge. And I take these pictures and I stitch them together, and I can use that for bridge inspection. And the way bridges are inspected right now, for the most part, is some person goes underneath the bridge and takes a look. Right? So we want to protect the human from having to get into that dangerous situation. Right? We've actually tested this system a few times. Works pretty well. So what we do basically from an input shaping perspective is we have some knowledge of the properties of the cables. We have some knowledge of the properties of what we're actually using for inspection. And from that, we can get some knowledge of the natural frequencies. And it's actually plural in this case, not just one. We have multiple modes of oscillation. Right. We also can use that system for something like you see here. So this is one that's in my lab. This is really kind of lab scale version of that cable system. So there's cables up here that are controlled by these motors that you can see. They go up over and then down to this guy. And our cables are not long enough where the cable itself will stretch. So we just added a simple pendulum to represent the flexible mode of the system. Right? We can change the length of the pendulum and the properties of that system and things like that. So actually you can imagine in other piece of this work, and what's relevant in Louisiana is maybe inspection of huge chemical storage tanks. So I could put this system on the side of a chemical storage tank and move this around to inspect the tank. Or I could put this system on a skyscraper and then move the robot up and down the skyscraper to clean the windows or paint the surface or do some inspection. And we still get in the case, however, we have vibration. So here's a kind of just example, really simple example of this system. So we're going to move it around just by controlling a joystick. And we did this input shaping thing to my joystick commands. And you see that even these simple kind of point-to-point moves, you get some vibration of the pendulum. And we also get some rocking of this plate. Right? Then we're going to turn on the input shaper, and we just designed the input shaper for the pendulum. Right? So you see the rocking of the plate doesn't go away. I haven't designed an input shaper for that in this example. It's just the pendulum I'm able to move around without much vibration. We can and we do design the input shaper for the rocking of that plate too. But that's not in that video. Okay? I will walk through the slides. So this is that process we talked about already. We need to know these things. We talked about convolution of impulses. I'll make sure these notes get posted. So another set of these for you to review. If you're interested, we just talked through this one on the board. Okay? Implementing input shaping is actually really, really similar to what we did on the board. So if I have some digital controller, just like we have for the PID controller, I can sample my input at discrete steps. All right? And all I do at every one of these steps, I take my user, the original reference command at this time step, so kind of R of K, the kth time step, and I multiply it by the first impulse, and I do that part right now. And I take my original reference command, multiply it by the second impulse, and save it for later. Okay, so it works exactly like we did, and I just march through time and keep doing this forever. So this is the process of doing this in real time on a real controller. And it's no different than how we constructed the original curve. Right? So I take a little bit, I take my step now, multiply it by this guy, take it, multiply by that one, and save it for later. And then you might get to a place like we do here, where I had a little bit saved for later, and I have a little bit from right now, I just add those two together. So it turns out this is really simple to do. Even the simplest, cheapest microcontrollers we can get can do this input shaping thing in real time, no problem at all. Because it's just multiplication and addition. There's no complicated math to implement this input shaping. So here's actually an Arduino. And on the top, this is actually sending out the output of the Arduino over serial to my laptop where I can print it out. And what you'll see is me pressing the button. And on the bottom part are the two components of that. And then the top is the input shape part. So I press the button. In this case, you get these kind of input shape commands at the top. So Arduino can do this no problem at all. Right? And you can even get cheaper, slower, less complex processors than Arduino. It's still possible to do that. And it does this, it does input shaping no problem as well. Right? So it's a really big benefit to this method that it doesn't take much processing power at all to implement. Okay? One thing we have to do in real time, basically, we don't have infinite memory to store that, so we actually use a ring buffer. And I'll kind of skip through this quickly, but you can check out the slides. If you have questions about that, feel free to get in touch with me. I can explain. The vibration equation, I want to make sure we see the examples. We had these positive shapers. So this is the ones we looked at so far. Right? We looked at these positive impulse shapers, input shapers, where we had the vibration equation. We limit all the impulses to 1, and we make sure they're all positive. Right? So we've seen shapers of this form so far only. Okay? And the result in the commands like we've seen so far. The other example, and we'll kind of touch on this briefly, the other most common example is called unity magnitude input shaper. So I still force the impulses all to sum to 1, but instead of them all being positive, I force them to alternate between +1 and -1. They have unity magnitude. Okay? What do you think the benefit of that is? Of letting them have negative amplitude? They're faster. Right? So for the same vibration constraints, a unity magnitude input shaper is going to be shorter in duration than a positive shaper. So our response will be faster. And you end up with commands that look like this. So if I have my original step command, the convolution works the same way. I multiply by this one, do that now, multiply by that one, wait till later, multiply by this one, and I get a command that looks like this. The other benefit, and the other place where using a unity magnitude shaper is beneficial, is if I have some kind of on-off system. If my system's only capable of 0 or 1, let's say. Right? If I look back to if my original command, my system's only capable of 0 or 1, and I try to use a ZV shaper, I can't, because I have some intermediate step that my system is not capable of. However, if I use a unity magnitude input shaper, you'll notice that my original command was 0 or 1. It was safe for my system. And now my UMZV shape command, my unity magnitude shape command, is also safe for my on or off system. So you see kind of input shaping research papers for satellite control. Quite often we'll be using unity magnitude input shapers. My satellite thrusters are quite often just on or off. There's no in-between rocket power. Okay? There's also somewhere in between, which is a big part of my PhD work, was this kind of in-between shapers called the specified negative amplitude. So instead of forcing it all the way to -1, you let there be just a little tiny negative impulse. Right? So it's not -1 now, it's some smaller little impulse, negative. Right? And you can get commands that are kind of in between a ZV and a UM shaper. Of course, we know some of these closed form. You saw these two guys already. We'll skip over that for now. And we saw we can measure robustness. Right? So you saw the ZV and ZVD. If we look at the unity magnitude version of those two shapers, so the UMZV and the UMZVD, you see that near the design frequency, they're basically the same. Okay, so our sensitivity doesn't change so much if we allow negative impulses. However, you'll see that the UMZV shaper is 1/3 of a period long, where the ZV was 1/2 a period. So we do gain the speed, like we said there. It's one thing to be kind of concerned about with the unity magnitude shapers is you are kind of pushing and pulling your system much harder. So you can excite higher mode oscillation. So if you look at the sensitivity curve way out here, the unity magnitude looks way worse than the positive shapers. So it's something to just be aware of. The kind of final, most general form of the shaper we'll talk about today, and this will come up a little bit tomorrow when we're looking at alternate ways to get to this shaper solution, is a specified insensitivity shaper. And what this does is say, well, I know my frequency, my system is changing in this way. Right? So I know that I want vibration less than VTOL from 0.8 all the way over to 1.2. And rather than limit the vibration just at one point, limit the vibration at m different points in this curve. Right? So far we looked at limiting vibration only at one frequency. And the robustness, the insensitivity we got was just kind of an accident in some ways. Right? In this case, what we're doing is specifying the insensitivity directly. So I take this vibration equation, that's the one we just solved, and so far we've been solving just for one frequency. And I solve it for m different frequencies, natural frequencies. Right? And that m, in theory, actually you need infinitely many for this to work. In practice, you need not very many at all to get a solution for this that has low vibration over whatever range you specify. What's nice about this is that this specified range, this range that I defined from omega-1 to omega-m can be whatever I want it to be. I have complete control over that. Right? The penalty for making that larger and larger and larger is that the time of my shaper gets longer and longer and longer. Right? So the more insensitivity you want, the longer your shaper is going to be. Okay? We can look at these things. We also can look at sensitivity to damping ratio. The reason we don't talk about this so much is that these shapers are much, much less sensitive to damping ratio than they are to natural frequency, errors in natural frequency. So we almost always just kind of stay on this axis. Right? So we're not so sensitive to errors in damping ratio. We can also look at this trade-off. So I mentioned the more insensitivity you want, the longer the shaper duration. So the axes of this should be probably flipped, but this is how we do it. So the vertical axis is the width of that curve, the insensitivity, and the horizontal axis is the duration. And here we're just normalizing by the damped period. Okay, so we saw so far a ZV shaper is 1/2 a period long, and we got 0.06 of insensitivity. Right? We saw the EI shaper is about one period long, and we have about 0.4 insensitivity. And then there's some other closed form shapers we know, a 2-hump EI, a 3-hump EI, some other ones up here. Okay. And what we see is that the SI, like we said, we can design it for any insensitivity we want. So that's why we show it as a curve. Right. And what this curve shows is there is some kind of optimal trade-off between duration and insensitivity. So for example, you wouldn't want to design some shaper to be here. Right? Because if you just let your duration increase a little bit, you get a lot of robustness, a lot of insensitivity for that change. Right? So if you're right here, you can just add a little bit of duration and get a lot of robustness, a lot of insensitivity for that change. Right? So in this lower part of the curve, what you really want to do is a ZV or an EI shaper. Is the kind of moral of that story, I guess. And then even up here, there's not as dramatic a trade-off, but these EI shapers, these ones we know in closed form, are kind of the time optimal solutions for that amount of insensitivity. Okay. If we allow negative impulses, so this is just the positive shapers. If we allow negative impulses, you see everything just kind of shifts to be shorter duration. Right? We have unity magnitude versions of all those shapers I just showed before, but now actually they're no longer time optimal. Right? So if you're going to use a unity magnitude shaper, you kind of probably want to solve the full optimization problem and not use the closed form solution. I mentioned those SNA shapers that kind of developed during my PhD thesis. You go from a positive SI shaper here in orange. If you allow just a little bit negative impulse, you get a lot of savings in duration. So even allowing a really, really tiny little negative impulse can get you a lot of time savings. So there's some benefit there. General design procedure for these input shapers, I think it's pretty straightforward. Basically, you need to determine your nominal system parameters. What's your dominant vibratory frequencies? Quite often, there's only one mode that really matters. Sometimes there are more. And then you need to know your associated modal damping ratios as well. So you need to know natural frequency and damping ratio. Right? Then you need to determine how much variation is there in these parameters. How much error is there in my estimate of those natural frequencies and damping ratios? Or how much is my frequency changing while my system is operating? So for example, the crane, right? As L changes, I start hoisting up or hoisting down, the natural frequency changes. So I need to figure out how much does it change so that I know how much insensitivity I need to change as a natural frequency. Okay. Once you know that, based on the curves I just showed you, you can pick out what shaper to use. Okay. And then it's pretty easy, straightforward. We have all these shapers in closed form to just plug in and get the answers. Okay. So let's talk about a couple other problems where we use input shaping. So here's some high voltage power lines. I think this picture's from the US. So high voltage power lines from one city to another or from the power plant to the city. Right? And actually these get inspected pretty regularly. Right? The current state of the art for inspecting these is just some person that jumps on the cable and walks along it. It's kind of crazy. So there can be 500,000 volts on these cables, but these people just hop on. And what they do actually is kind of interesting, is they actually hop off of some helicopter, generally, onto these cables. It's kind of crazy. So the platform this guy is sitting on is actually off the side of a helicopter that you'll see in a second. So there you see him, he's kind of hanging off the helicopter. Pretty dangerous job, right? So we might want to have some kind of robot to do that instead. So here's one that was designed by my friends at this company, Hybot. Robot basically designed to ride along these power lines. Right. And what's kind of cool about this and what resulted in me helping them is all their kind of main weight of this robot is down here on this counterweight. And this can be moved forward and backwards. And they have some sensors that ride along the cables and try to sense the health of the cable. So this robot is pretty cool. They've tested it on real lines. And what's cool about it, what's really nice, is that it can get around the towers. So imagine this would not be so useful if I had to go up at every tower and pick it off and then move it around to the next tower, around to the next section of cable. So I can get over these spacers, and you'll see it can go around the tower as well. So what you're going to see, the suspender clamp they mentioned there, is this guy is what hangs from the tower to suspend the cable. And to get around it, you see it kind of moves that center of mass backwards, pops a wheelie, moves the cables out, then it moves it forward, and spins out again. So that's how it gets around the towers. What you might have noticed from that video is they kind of cut out some frames. And they cut out some frames because when it's in this mode, right, so the center of mass is kind of back there, and it's in this mode where it's only two pulleys, it's actually really easy for this system to start rocking. Right? So if you have some wind blowing, or even just driving this when it's in this kind of acrobatic mode, will cause this system to rock. And so it looks something like this. So we get to the hanger, and you'll see it kind of shifts this counterweight backwards, which is going to cause it to kind of pop the wheelie, and the front wheels will come off the cable. But once that happens, this system can rock quite easily. And you see when we start driving, you can get quite a lot of rocking if you time your driving the wrong way. So you see the system rocking. And now we stop, it's going to rock even more. Right? You can imagine that that's going to be troublesome for this system. Right? You don't want this kind of rocking when the system's 100 meters or 200 meters above people that might be below. Right? So not a safe condition. So we take this system and apply input shaping actually to that driving now. And we take that same system, and this is a full simulation, and we stop, no vibration. So we basically just applied input shaping to the driving of these pulleys, knowing what the rocking frequency was. What's cool about this input shaping, so far we've only talked about one frequency, is that it's quite easy to do for multiple frequencies as well. So here's another crane at Georgia Tech, and same crane you saw before actually, but a different kind of payload. So this long kind of skinny payload, what you'll get is not just pendulum motion, but string type vibration. So you'll see in some cases that the weight and the hook will be moving in opposite directions. And actually really expert crane operators still have trouble with this one. Right? In this case, it's not really an expert, it's just a student. And he's trying to move this payload around and to end this circle. Okay? And he's working really, really hard because there's $200 prize for the fastest time. But you see there's kind of a lot of vibration already. Every time the video faded through black or fades through black, that's 1 minute we took out of the video. So it takes him about 3 minutes and 50 seconds to complete this simple little move. So if I have this multiple mode of oscillation, it's pretty easy actually to design a shaper for more than one mode. Right? So I take one mode, the kind of pendulum mode of that vibration, and I design an input shaper for that frequency. Right? And then I can take the other mode, the second mode, which is kind of string type vibration. I can design a shaper for that frequency. Right? And then I can take and just convolve those two shapers together. And I'll get a new shaper that gets rid of both vibration at both those frequencies. Right? So if you know how to design a shaper for one mode, you now know how to design it for two modes, and you just keep repeating and repeating. No problem at all. Right? And this works because we can look at those sensitivity curves. They combine, they actually multiply in the frequency domain. We can look at multimode SI shapers as well. So the SI shaper, remember I picked the kind of points in the range I want. So if I have multiple places that I want low vibration, I just define multiple ranges where I want low vibration now. Okay. This is actually going to be faster than the convolved version. So you can we'll look at the end of his move again, and then this is actually using one of those two mode SI shapers, the next move. So 3 minutes and 50 seconds without input shaping, and now with input shaping, you'll see it only takes 11 seconds. Exact same crane 30 seconds later with this input shaping stuff applied. We'll also see that you can extend it out. So I did some work with Boeing. on cooperative crane control, so moving multiple cranes together. So there's one example trying to move this really long wing, it takes more than one crane. So here's one crane, here's another, and then actually attach a couple more. So we can look at controlling these multiple cranes with input shaping as well. So actually this is some work I did when I was still at Georgia Tech too. So you see I'm moving these 2 crane trolleys together. And actually in this case we only get one mode because it's a 4-bar linkage. It's pretty straightforward. Even a simple move like this can get you some vibration. And we can apply input shaping to that and get basically no vibration. Pretty straightforward, nice simple result. However, if we move in the other direction, in the bridge direction we would say, I actually get 3 modes of oscillation. So I kind of have the 2 cables and then this guy oscillating that way. And I can take it and I know those 3 modes of oscillation now. What I can do is take those 3, design input shaper for that, and move it this way and still get really, really low vibration. And you see not 0, but almost 0. Okay. All right. I think that's all I have for today. So tomorrow we're going to take this input shaping idea and discuss a little bit more, and then discuss actually a little bit of reinforcement learning, and probably some model predictive control. So 3 kind of modern approaches, continued modern approaches to control. So I'll see you guys 10 o'clock tomorrow. Thank you.